First of all, thanks for giving me the opportunity to present some of the work that we do in San Diego, but many other people are doing around the world. As you can guess, I'm not a native speaker. I come from Italy, I'm from Rome, so if you don't understand something about my presentation, just raise your hand and I will try to clarify. And then I would like to thank, obviously, the TSRC for giving this opportunity and Julie for this nice presentation. So, as Julie said, we are a theoretical computational chemistry group, which means that we don't have real labs in, as you see, San Diego, but we have a lot of computers, and we use math and physics to try to model reality. And I will try to convey the message that maybe we are close to really reach that kind of realism that we need in order to model on a computer what my colleagues can actually measure in their labs. And so that will help guide experiments, but also will help speed up the discovery process. It will also help to reduce the cost of any discovery, because we can probably do a lot of things on a computer in a cheaper way. Okay, so why we need to think about water purification technologies? And these come from a very few facts that you can find on the website of the United Nations. And so, first of all, there are already 2 billion people that live in areas of water scarcity. Around 700 million of people suffer right now, today, for water scarcity. 2/3 of the population live in areas that experience water scarcity at least 1 month a year. I come from California, although I'm not from California, and we have been on a drought for a long, extended period. And California is a well-developed state, right? By 2025, if everything stays as it is now, there will be 1.8 billion people that are expected to be leaving their countries. And to be living in regions and countries that suffer water scarcity. And this means that there will be a lot of people that can be displaced just because of the needs of pure water or drinkable water. Okay, and already now, if you think about water that is in the ground, most of that water is already being used a lot. And so many of these, yes, as I said here, 1/3 of the world's biggest groundwater system are already in distress. So we cannot keep exploiting those groundwater systems. Okay, and so I want to quote here Isaac Asimov, who was actually a biochemist, that pointed out a long time ago that this is a problem that affects everybody. It's not just a problem of one nation or one country, one state, one person, one family, one city. It is a problem that affects all of us, and so because of this, we need to come together in order to address this issue. And so we as a scientist, and especially as a computational chemist, it's very hard to reach this kind of reality, because we are used to work with small molecules on a computer simulation, looking at small things and how they behave on a landscape that I will show you is very small. But those processes actually are going to affect the macro-scale system that I will show you in a few minutes. And so understanding how nature behaves at the fundamental level is actually key to inform engineering discoveries and the construction of what I will tell you about that are like desalination plants. Okay, so as Julie said, we have a lot of water around us. In San Diego, we can just watch outside our window and we see a lot of water. Unfortunately, we cannot drink that water. So 70% of the Earth's surface is covered by water. Obviously, it's not drinkable water. However, we can engineer systems that can make that water drinkable. And just a few miles north of San Diego, there is one desalination plant. What is a desalination plant? A desalination plant is a plant that takes water from the ocean and then purifies that water to make it drinkable. And I will show you how that works. So this is a desalination plant in Carlsbad. And it was it started its operation in 2015, at the end of 2015. It cost about $1 billion and takes about 100 million gallons of water per day from the ocean and from that makes about 50 million gallons of drinkable water per day. And it serves about 500,000 people in San Diego County. How it works? So, water comes from the ocean, enter here, it goes through two different pre-treatment, this one and here, and then enters this white region here, where actually the water is separated from salts, and then the drinkable water goes here for a post-treatment, so in order to make sure that water is actually ready to be distributed, so there will be other treatment, add some chloride and some other minerals, and instead the brine, so the water that contains the high concentrated salts, is discharged to the ocean again. And of course, before discharging, this high concentrated water is diluted with ocean water so that the impact on the environment is negligible. Otherwise, if you put a lot of high concentrated salty water in the ocean, you will destroy the ecosystem of the ocean nearby. And so the process where all this magic happens is called reverse osmosis. What is reverse osmosis? It's something that looks like this. So this one is osmosis. We have pure water on one side, salty water on the other side, and the membrane. Naturally, so spontaneously, this membrane only allows water to come through. So spontaneously, if we don't do anything, water will actually go through the membrane and will try to dilute the highly concentrated part of these solutions. So this happens without any work. However, what we want to do is the opposite. We want to take water from the salty part. And so in order to do this, we need to apply high pressure on this side of the solution so that we force water to actually go to the opposite direction and so go into the pure water part. And so here is the problem, because obviously we want to revert what nature does spontaneously. And so in order to do this, we need to pay. And the pay comes from the fact that we need to apply a pressure that is very high. And so in order to apply pressure, we need to spend energy. And the amount of pressure that we need to apply is proportional to the efficacy of our membrane. So if our membrane is very selective and allows water to be separated by salts very efficiently, then we need a lower pressure, which means that we need to spend less money to actually make this reverse process going. And so now if you look at what happens here at the membrane, these things are actually molecular level, because now we are at a scale where molecules and ions, so small objects that are 10 to the minus 10 meters, 10 to the minus 9 meters big, which is like 1 billion of a meter, actually behave and pass through these pores. And so now the things becomes molecular level. And so here is where fundamental science becomes important before actually going through the construction of the desalination plant. And so I will try to convince you in the next 5 minutes that there is a lot of things that we can do on a computer to help guide this process. As you know, we are living in or maybe we already lived, a computer revolution. Just maybe 50 years ago, in order to do small calculations, you probably need a room like this filled by supercomputers. Now the same calculation can probably be done on our cell phone, even much faster, right? Okay, and so there has been this progress, which means that computing power has become accessible, and there is a lot of computing power available. So we can use this computer power not just to post on Facebook or on Twitter, but we can use that computer power to actually do useful simulations, and I will tell you a little bit about, that can be used to guide experiments and maybe guide new ideas. And I will try to make this analogy. So the things that we are doing on a computer is very similar to what happens to video games. So this is reality. And for all of us that live in the 80s, we were very happy to play a video game like this. Probably for the millennial, this looks like prehistory, right? Because we are used to play something like this, right? And you can see there is a big difference. Realism is definitely here now. You can see the emotion of the fans. You can see players with different skills. You can see face expressions, emotions, right?
You will not get the World Cup right now.
Italy is not in the World Cup. Yes, I know. We will root for Germany. Actually, just a digression, because I was just reading today that machine learning predicted that Germany will actually win the World Cup. And actually it was a very complicated process, because the first choice is actually Spain. But then they went through a different level of machine learning and actually showed up that Germany has higher probability. So it should be Germany. So we will see if what I'm going to tell you about is actually predictive enough. But we can do science, so this has nothing to do with soccer, right? Okay, but the point is that we can actually have realism into a video game. And the computer simulation is very much like a video game. But now we use laws of physics to model what nature does. And so here is our glass of water. On a computer, this looks like this. And you can see now that we can actually watch individual molecules moving around in our glass of water. And so these molecules are actually moving not just randomly. They move because there are some forces that act on them, and they try to arrange themselves in order to minimize their energy. They want to be as happy as possible, so they don't want to have any distress, right? Okay. And so this looks like a video game. But now from this, instead of winning points as in a video game, we can learn about physics, because we can learn what molecules do when they are, for example, next to a membrane. We can learn about how molecules behave near an ion and understand how hard it is to separate a water molecule from an ion, because you need to break some interactions there. Okay. And so now what is a computer simulation? This probably is very familiar to you. And a computer simulation really looks like going through a mountain landscape. So in a mountain landscape, you have valleys, you have mountains, you have passes, and you have a lot of trails, right? So you go on a trail, and you walk around, and you go up or down, depending. In a simulation like this, molecules do exactly the same thing. Instead of having a mountain landscape, we have what we call an energy landscape. And so each configuration of the molecule that I show you in the movie corresponds to a point in this energy landscape. There are configurations that are in the valleys, so they have a low energy. There are configurations that are on top of the mountains, so high energy. And in order to go from a valley to another, you need to go through some passes. And that is exactly what a molecular simulation does. And so we follow what we call trajectories. So we follow molecules over time to see how they behave and how they change depending on what the environment is around them. Okay. So now the problem is how we calculate this energy landscape. In order to have a simulation that is realistic, we need to have that green landscape. We need to know where the valleys are and where the mountains are. And so there are two ways to do this. We can do this using classical mechanics, and this is Isaac Newton, that probably is familiar to all of you, that essentially started what we call the field of classical mechanics and classical dynamics. Based on these ideas, and I will try to be as pictorial as possible, a molecule, this is the only equation that is there, a molecule like water can have bonds that are made by these elongations here. So this is an oxygen atom, these are the hydrogen atoms, and these atoms can actually jiggling that way. And so they have a symmetric stretch and asymmetric stretch, we call it. And then they can also bend, right? And then when you put molecules together, they can actually also interact. It's really like a human behavior. When you put two people together, they start talking, or if they don't like each other, they go away, right? The same thing is for molecules. Sometimes they attract each other, sometimes they repel each other, okay? It's a very nice picture, this, but it's not very close to reality, because we know down and close to our heart that this problem is too simple, unfortunately. What we need to solve is what Schrödinger, at the beginning of last century, told us to do. Electrons at nuclei, so protons, neutrons, when they are at very small scale, do not act as normal objects. They behave what we call a wave behavior. So instead of having balls and sticks, as I showed before, you have a wave, like a wave in the ocean. And so already thinking about the wave in the ocean, you can immediately see that you have a front of the ocean, but you really don't know where the front starts, right? Can be kilometers long. And the same is true for the wave function in the quantum mechanics. Knowing this wave behavior of atoms and molecules is very difficult. And what we need to solve is what is called the Schrödinger equation. And so instead of having balls and sticks, we have a fuzzy density that describe how the electrons are moving around the nuclei at any given time. And they're always moving. And knowing how to represent this density is very hard. And so here is the problem. Because classical mechanics is not very accurate, and this problem is very hard and very expensive. And so now we are in trouble, because we want to simulate, as I mentioned at the beginning, water that goes into the desalination plant. So it's a very ambitious project and goal. And now I'm telling you that we are already problems in describing like two molecules interacting together. But now we realize something, right? So how can we do this? In our group, we realized that if you look at when these two things have been developed, so the best way to solve the Schrödinger equation is in 1966. And the first expression like this one was put forward by Lifson and Warshall. Warshall won the Nobel Prize in Chemistry in 2013. It's also more or less at the same time, 68. And so now if you go back in the 60s, we were like this. Mulliken was winning the Nobel Prize in Chemistry exactly for his work on chemical bonding and electronic structure. There was the first man on the moon, and everything was about peace and love. In the 2018-ish, things have changed. In 2013, as I mentioned, Karplus, Levitt, and Warshall won the Nobel Prize in Chemistry exactly for their work that they were doing in the 60s and 70s. It takes some time for the community to actually realize when the work is very good, right? We know that there are people that want to put all of us in the space, maybe to Mars. And so we are talking about commercial space flight. Here was like a victory, one person on the moon. Now we are thinking about, okay, we go all on Mars. And then for the youngest people, we don't go to Woodstock anymore, we go to Burning Man, right? And probably many of you are already arranging their van and their art exhibit, right? Okay. And so what we can do? We need to change something. We cannot keep doing the same things that we were doing in the 60s. And so what we did was say, okay, let's think about how we can put together chemistry, physics, and computer science, and trying to exploit our knowledge of chemistry and physics, and combine that knowledge with the computer revolution that I mentioned before. And so what happened? It happens that computers, we know, now can learn about human behavior, right? It's on the news, what the social media can do with the information. But we can also look at the bright side of this. So computer, and when they learn, we call them machine learning, because the machine is learning from data that we provide. And data that we provide can be books that we like or dislike, music that we like, dislike, restaurants, sports, cities, and things like that. And the machine acquires all that information and then start making a profile of each of us. And so it tries to fit and to predict what we will really like tomorrow, or in a week, or in a year, based on what we liked before and what we didn't like before. And this is how all the advertisement works on Google, Amazon, Facebook, Twitter, Yelp, right? Okay, so we can use the same approach, the same algorithms, to learn about molecular behavior. And so here is a pictorial cartoon of a glass of water, for example. You have a lot of water molecules, and they are all interacting through what we call hydrogen bonds. If you want to know more about this, next month there will be a workshop about the challenges that we are facing in order to understand the behavior of water here at TSRC. Okay, and so these molecules, this configuration here, this picture, correspond to a point on the energy landscape that I showed you before, okay? And so this molecule will keep moving on that energy landscape. And what we want to know is that energy landscape. How can we do that? We can start thinking that each of these molecules may be isolated. So let's imagine that around that molecule there is nobody. Like here, you imagine that nobody is around you. And so you have your identity, and this molecule has its own identity. It's stretching, it's bending. And there are many different molecules in this picture, right? All of them are slightly different, as all of us in this room. We are all slightly different. Then we put another molecule next to us. So we put our neighbor next to us. And our behavior changes because we are not alone anymore. We need to understand that around us there are other people. And the same is for the molecule. This molecule now cannot do whatever it likes because it has to feel that there is another molecule there. And so it needs to go on the valley now that is made by these two molecules. And there are many different two pairs of molecules, right? And all of them has to get together. And then there are three molecules. And again, if you think about how molecules interact, it's very similar to how we human interact. We have a friend, we start talking, another person comes. Our interaction with our friend changes because we have a third person. The molecule is the same. These two molecules were interacting, and now we have an extra molecule that is changing this interaction because it needs to talk to the other two as well. And so we call this, so these interactions now involve three molecules. And we have many different triplets. And we can keep going this way, 4 molecules, 5 molecules, 6 molecules, until we reach n molecules, right? And so now what we can say is that the energy of this configuration that contains n molecules can be written as a sum of energy of isolated molecules, all of them individually, plus all possible two molecules that we find, all 3 molecules, 4 molecules, 5 molecules, and we call this many-body expansion. And that was our contribution to the field, because we figured out a way to use machine learning to derive sets of all possible dimers, trimers, tetramers that are representative of the behavior of water in any condition. Exactly like machine learning predicts what I like to do tomorrow, which restaurant I like to visit tomorrow in Telluride, what kind of book I want to read. Because it figured out from the data that I provided how I behave. And the same thing is what we did. And so then we exploited computer power that using these classical mechanics, the things that are not very accurate, now allows to study millions of atoms. We use the same computer power now to build new models that are machine learned that go after accuracy and prediction. So we can use computers to actually make predictions. And so just some history, the first simulation of water on a computer is from 1971. In 2016, we showed that our model, that is called MBPOL, is able to reproduce the water properties from an isolated molecule in the gas phase, in the atmosphere, to liquid water, to ice, to interfaces. And so now we are at the point where we have an ocean, but we also have a pretty nice representation of that ocean on a computer. And so now we can actually understand how the ions and the water molecules behave in nature just by watching a movie on a computer. This is pretty good advancement because we don't need to go, even if it's close to us in San Diego, we don't need to go to the beach. We don't need to spend money to build instruments that allows us to study what water does there, but we can try to model this on a computer when the system is an idealized system, which is what becomes after the water goes through the pretreatment in a desalination process. Because after the water goes through this pretreatment, what we have in the water are just, in the water that must be purified, are only water molecules and ions. Okay, and so now the becomes this one. We just don't want just water, we want also water in contact with the membrane. And this week I am at a workshop that is mainly interested in studying how water behaves when it's in contact with different surfaces. And so now what we want to study is how this water interacts with ions and how the water can go through these small pores here in order to be filtered. Okay? So this is an idealized membrane. It's made by graphene with pores inside. It's what is called perforin, and is patented by Lockheed Martin. It's probably not very efficient, but works very nicely as an idealized system to study water desalination. Okay, and so now the goal is to find materials that can actually allow us to desalinate water. And so in San Diego, we are working on special type of materials that are called metal organic frameworks. You can imagine, you can think about metal organic frameworks as made by small pieces of Lego. There is one big piece here, which is made by metals and act as a node. And then there are linkers that are made by these organic molecules. And then you combine them, you combine these things together, and you make a porous material. And this porous material can extend for micrometers. What does it mean? It means that now we have materials that have a well-defined structure and are porous, which means that allows molecules to get through. And so this is pretty interesting because now we can try to model how water goes through these MOFs that are highly designable because we can change these nodes and we can change these linkers. And through chemical synthesis, we can actually modify the properties of this material in order to make it more efficient for water desalination. And there are many different beautiful structures that you can make with this MOF. Essentially, if you go back home and you go to Google and you Google metal organic frameworks, you click to images, you will find a beautiful collection of possible structures that have many different shapes, many different properties. And so now what we can do is to have one of these MOFs and start bringing water inside. You can see that everything is moving, and then we bring water inside. And now we try to study how water diffuses through these pores and how ions can get trapped into the pores so that we can just get water at the end of the material. And so this, again, is a very nice problem for machine learning. Because what we can do through simulations is to calculate quantities that are directly related to selectivity and transport of water through these pores. And we can relate these properties to what we call in machine learning descriptors. So properties of the material that directly affect the quantities that we can measure, and so that we can calculate. And so through this, we can actually use computers to make new MOFs, which means that we can design many different structures that are not even synthesized yet, and use the same simulation to screen those structures so that we can get our optimum material and go next to our synthetic chemists that can actually try to make the material, test it in a lab. Hopefully they will find the same performance as we find in simulation, and then go to an engineer that has the job to scale everything up, because we are talking about lab experiments, computer simulation, and then the problem is to make these materials extended enough so that we can actually use this material for water desalination. Just to give you an idea, in the desalination plant in Carlsbad, there are many different sectors of this where the reverse osmosis happens, and each of these sectors contains 16,000 reverse osmosis membranes. And so we need a lot of these materials that are assembled in particular ways so that can efficiently separate water from ions. And so, just to conclude, I hope that I convey the message that, first of all, computational chemistry or physics is cool and is fun. You can learn not just about physics and chemistry, but also about computer science, which probably gives you a lot of opportunities as a job afterwards. But what is important is that using basic science, we can inform technologies that take place on length scales and time scales that are order of magnitude larger than what we can stimulate or study on a lab. But they actually work because of the chemical and physical processes that take place at this small scale. And so before concluding, obviously I need to acknowledge all the support that I received from different agencies. So UC San Diego, obviously, the National Science Foundation, Department of Energy, the Air Force Office of Scientific Research, the Army Research Office, a lot of computer power. And we use what is called XSEED, which is a distributed computing facilities funded by the National Science Foundation, and NERSC, that is instead funded by the DOE. And of course, my wonderful group, because obviously nothing would have happened with the help of many bright young people. But I would like to also mention that all these funds that actually come through these agencies actually come from all of you. And I'm happy to say anytime that I have millions of investors in what we do, because essentially we have millions of people around this country that are happy to contribute with their taxes to basic science. And with this, I thank you for your attention, and I'm happy to answer any question that you have.